I think
It's your phone.
here.
Okay. Perfect. Thank you. Thank you so much. I'm sorry. Before starting our session, I need to check the attendee who is online. Hello, Julio. Can you hear me?
Yes, I can hear you. Can you hear me?
Yeah, I can hear you say something, but how to volume up? Something is. Say anything once again. Anyway, he can't hear me, so please contact him directly. Okay. Okay, it's exactly 3:30, so we promised. Hello, everyone. My name is Jae-Yeol Cho. I'm the chair of the TC29. As you know, the title of the TC29 is the Network Construction and the Joint Utilization of Large-Scale Experimental Testing Facilities. Our TC29 began its activities with approval in the spring of 2022. As of now, we are 1.5 years old. 8 years and a half have passed. Okay, yeah, passed so far, but the committee members have not yet been formed. The reason is that the TC29 is really different from the technical committees, other technical committees. The reason is that the TC29 is the purpose is quite different from the conventional technical committees. Normally in technical committees, it is common to produce a constructive result through academic and sometimes practical discussions on a specific topic. In contrast, the ultimate goal of our TC29 is to provide a kind of a service. Something is coming out from my phone. Yeah, sorry. So to help you understand, I will first talk about the purpose of our TC29. The first is to build a network of world-class large-scale experimental test facilities and share the network with the ASCE members. In other words, it provides the ASCE members with easy access to the network. Of course, in addition to joint use, one of the ultimate goals of our session, our TC29, is joint research using the experimental results produced in our network. As can be seen from the purpose of TC29, both provider and potential user of experimental facility are eligible to become members of TC29. In our session today, we have 5 valuable presentations from ASCE, CICHE, JSCE, and KSCE. I believe that These four societies will be potential provider of experimental testing facility. So I have prepared a venue to introduce each society's large-scale experimental facilities to our ASCE members. 4 of the 5 presentations will be given here in face-to-face format, and Professor Julio Ramirez from the ASCE is currently online. It's now at 3 a.m. In the Eastern Time in the United States, where he is located. Julio, can you hear me?
Yes, I can hear you. Good afternoon for you and good morning for me.
So I have a technical problem still. Okay.
Can you hear me?
But anyways, I'm truly sorry about and thank you for participating in person, even remotely. Now let's start the presentation. The first presentation is by Dr. Chung-Che Chou from CICHE. He's a professor at the National Taiwan University at the Director General of the National Center for Research on Earthquake Engineering. We call it NCREE. Over the 5 presentations, I think only this one may contain some academic content. However, I believe that Dr. Cho will tell the story interestingly so that even some majors can understand it. So with a big round of applause, let's welcome Dr. Cho. I'm going to use your machine.
I think it's always easy for me to stand here to talk about the work we have done at NCREE. So as you can see from the first page, at NCREE we have 2 labs. One is the lab very close to here, about 10 minutes driving. It's our first lab established in 1980. Then we have a second lab in Tainan, which is about 200 kilometers from the Taipei. So you can take the high-speed rail from Taipei to Tainan by about 90 minutes. So I will use a few research topics to introduce you what the facility we have in Taipei and in Tainan lab. So first of all, I want to use this project. This is a project conducted from 22 to 23. So it's a full-scale 3-story steel frame using the so-called moderately ductile column in seismic area and the all steel BRB. So this is international collaboration between the National Taiwan University and the University of California, San Diego, of Wang and the Georgia's Thames Plus, and the University of Texas at Arlington, and also the National Chung-Che University, and also NCREE for this project. So why do we want to study this particular problem? Because if you are familiar with the ASCE seismic provision, which is a US code on the steel, so they have the 2016 version and also 2022 version. Particularly, we are looking at the changing for the column. For example, in 2016, it requires the column B/T ratio. For example, in Taiwan, we are using the rectangular column, so the column has a width and the thickness. So in the code, it requires a minimum width-thickness ratio to be meet the highly ductile member. What does that mean, highly ductile member? That means when the building is under earthquake, this member will go very significant inelastic formation. We call it highly ductile member. But how about for the moderate ductile member? That means in a very strong earthquake, it only gets very minor inelastic formation. So you can see this B/T ratio is almost like doubled. But in the 2016 become 2022 version, it's become more stringent. Then particularly in the older version, it requires we can use a beam and the column satisfy only the moderate ductal column, the member requirement. But for the 22 version, the beam and column should be designed by this, not by this. So you can see the value, it reduced half. That means your thickness will be doubled if we follow this new version of AIC size provisions. So this is very strict and it's over conservative. So I was this research to talk about this. So in order to do this, so basically we designed a three-story frame with one special moment frame and the other is a buckling strand brace frame. So you can see this B/OVT ratio based on Young's modulus, material strength, you get a 22 for the moderate ductile member. And so our column basically satisfies this. B/OVT is very close to the requirement of a moderate ductile member. But as you know, Taiwan is in a high seismic area. Basically, we should follow the more strict area. But in this case, we try to use this less ductile column to see how it performs in shaking table testing. Because that's a BRB, the buckling strength brace frame, so this is one of the BRB we used in our testing. So basically, we have a, we call it the core, center core to take the actual force. But as you know, when the plate is under compression, it's very easy to buckle, right? So we put the so-called restraining member, that's all blue part, and use both to sandwich them together. So this is how we do. But usually, in a very popular way, they put the concrete inside in order to make the more rigidity. But in our case, we all use a pure steel without putting any concrete inside. So that can take about 50% of the construction labor and also save a lot of money. So this is one of the testing we conduct. So you can see we have a 50-meter high reaction wall in our Taipei lab. So with 5 actuator, each one is 1,000 kilonewton capacity. So we put the SBRB over here. So this shows the actual force versus actual displacement response. So it's very stable up to 2.5% actual strength. That's about the maximum considered earthquake level in Taiwan. So this has been used in many buildings. For example, one probably just 10 minutes away from here. This is a bank headquarters, and this is Yanping High School. It's also 10 minutes drive from here along this Jianguo Nanlu. And there is also the highest building in the New Taipei City. This is a 45 residential building. They use more than 800 SBRB for the seismic resistance. So this is one of the testing for this high-rise building. You can see this is without fill any concrete. So under the tension and compression, you can see here. So the all member perform very well. It reaches a capacity 7,000 kilonewton in compression and 6,500 kilonewton in tension. So the performance is very stable. So in addition to that, this is one of retrofit. This is a very old building, 30 years old. Is located on the eastern part of Taiwan, Hualien, Taitung area. That's the most beautiful area in Taiwan. So if you have a chance, please take a time to go to the east coast of Taiwan. So this is a 30 years old building. It's also the bank building. So they try to retrofit this old existing concrete building is SBRB. So you can see they put all the brace in the perimeter of this building. So this is the photo we took 2 months ago in the shop. Then they try to use this SBRB to install in this building. So in addition to SBRB, we also use our research funded to develop a different type of brace. So you can see this is one of the largest brace we are testing. If you look at this force deformation relationship, which is totally different than the BRB because there is no force deformation in this 2 corners, right? So this we call the self-centered brace. So it means when the loading is unloaded to here, it has no residual deformation. So that means this brace can provide energy dissipation and also the reduce the residual deformation to a structure. So this is the one without energy dissipation device. This is one with energy dissipation device. That's what we are testing in our first lab. In addition, in our first lab, we have a mass facility. So in this case, we test the column. So we can apply the more than 10,000 kilonewton actual load. Then we also have a horizontal actual load actuator over here to apply 4,000 kilonewton capacity. So you can see during the axial load and the lateral load, you will see the buckling, shortening of the current in this facility in Taipei lab, we call the MATS. So that's the current, the single current testing. But as you know, the current is connected to the second floor beam and also the second story current. So in this particular collaboration between the UC San Diego, Michigan and Harbor, so we are trying to incorporate the boundary condition between the beam and the current to simulate the real boundary condition in the building. So we take this portion, this is the current, second story beam, and the third story beam. Then we put the lateral support in order to make sure the beam did not have the lateral torsional buckling. So this is our actuator, put here, here, and also here. So we use the 3 actuators to do the very complicated testing. This is one of the, I think this is the first very complicated testing for the current in order to simulate the real boundary condition in the building. So let me show you one of the photo here, video here. So if you look at here, we also apply the axial load over here. Then we apply the lateral load over here. Then during this moment, axial load, you will see the buckling here. Once the buckling occurs, the current will shorten. So these 2 actuators needs to follow this shortening of the center current in order to make sure all the axial force can go through the center current. So that's how we conduct this testing in the lab with UC San Diego and Michigan and Harbor. So that's all the facility in our Taipei lab. You can see then in Tainan lab, we have one big shaking table in Taiwan. So the table dimension is 8 meter by 8 meter. The payload capacity is 200 tons. So that means we can put the 3-story full scale the building model. As you can see here, this is a steel dual frame system. And in this particular case, we try to use, you can see a precast lab. So basically the slab is manufactured in the shop. Then we just use the energy dissipation device to tie the slab to the building frame in order to speed up the construction at the site. So that's how we try to investigate the behavior of this so-called precast slab on the building performance. So this is how we construct this 3-story, 9-meter high frame in the lab. So you can see this is our shaking table. So this is our frame. The center frame is taking the earthquake resistance. So we assemble everything here with 9-meter high. So then we can leave here. Then we put the perimeter frame there. Then we put the first story slab, second story slab, and the roof. And we'll put the concrete mass over there. So during this testing, we try to only input the one directional loading. For this particular loading, we use the ground motion we recorded from the last year Chihshang earthquake. If you read the news, there's a big earthquake happened on the east coast of Taiwan. The magnitude is 6.4. So they are the first day, this epicenter is over here. Then on the second day, less than 24 hours, we get the second epicenter. A big earthquake happened here. So then we have one building. Since this energy propagated from the south to north, so we see some damage over here. In this particular ground motion or earthquake, we have 2 bridges totally collapsed and also 2 buildings totally collapsed. But we have several hundred buildings damaged. So for this 7-11 building, that's here, that's before earthquake. Then after the earthquake, you can see this 3-story building collapsed. So then we also have the accelerometer station over here, which is about 1 kilometer away from this damaged building. So we use this ground motion as our input to see what's damage to this new building. So in addition to building collapse, as I mentioned, there are 2 bridge collapse. So this is a almost 40 years old building on the East Coast. And you can see the red line represents the faults. All the faults on East Coast are running from the south to the north, but our bridge is going from the east from the west to the east. So when this earthquake happens, activate the fault to move from the south to east. So that's all the current very old bridge fall down without forming the so-called plastic hinge at the column base. So that's a Yuli station. So we record this ground motion PGA is a 449 Gale, it's about 0.5 G, and the peak ground velocity about 69 centimeter per second. This is a force period for this force pulse the ground motion. So you can see for this Yuli motion, when we draw the response spectra, that's the blue line. Without doing any scaling, it's very close to our design response spectra called the DBE line over here. Then we also collect the other 20 motions. So when we do average, so this average line very close to our design spectrum. So that's why we use this motion without doing any scaling for the DBE level. So that's how we recorded the motion. You can see this velocity pulse over in this 30 to 35 second ground motion, and there's a residual deformation over here. So then for this particular shaking table testing, we have two phases. The phase one, the slab can move freely with earthquake resisting the frame. In phase two, we tied the slab rigidly to the frame, so to simulate the original traditional building response. So for test phase one, so PGA run from the 0.031 G to 0.6 G. For test two, we run to 1.5 G. Our structure period is 0.5 to 0.4 seconds. Then for this three-story building, we have almost 570 channels to measure the strain, disformation, and we also use a mocap to capture the displacement. So this shows the velocity SA. So for this Yuli motion, that's a blue line. So for our test 7, so you can see the intensity is already beyond this Yuli original motion. Then test 8, we run to test 7. So this is about 2.5 times larger than the Yuli motion at the 0.5 second, which is a fundamental period of this building. Then there's called IP. IP is called the ground motion power. Basically, it's the energy divided by the second to measure the instantaneous power to the building, which is related to high damage to the building. So you can see for the original ground motion table, this is the power intensity. So for our test 7, 8, and 9, which is very large. So that means, so when we run the test to 7 or 10, so we can see it's already beyond the earthquake intensity we recorded last year. So this is, I just show you, since there are 17 testing, because of time, I just show you the test 10 in phase 2. For this, it doesn't work well. Okay, so I don't know why it doesn't appear because of a delay. Yeah. Give it the time. Okay, it's moving. Oh, it started moving. You can see this red point start moving. That's a base shear versus the roof displacement. Okay, this is recording during the test 10 with a 1G in the table. So you can see the roof goes to about almost 4% drift, which is very large for the brace frame, because in the code, the brace frame at the DBE level is 2%. If MCE level, that means in the design, it's 3%. Now we reach almost 4%. Then let's look at some detailed response for the SBRB, looking from the inside and the beam column connection, column base, and also this to see if you can see this. So you can see during the pulse motion, there's a big pulse to compress this SBRB. Then there's no buckling occurred. Then this shows a connection. This shows a column base. And also this is a reduced beam section for the beam. I'm sorry, there's it should have some noise. Okay, so we record the displacement from the test 1 in test A. Then you see when we run to test A, there's a big residual deformation about 0.5%. 0.5%, if it's 3 meter high, the building, you probably have like the 1.5 centimeter the residual deformation. Then in order to act more motion, so we reduce the motion to the other direction. So we bring this back here. Then we run another test into here. So that goes to like this. So the important thing is to see this, because in the phase one, the slab can slide relative to the frame. But in the phase two, the slab cannot slide, right? So what's the impact to the building? So you can see when we do the acceleration between the floor to the table, for the phase one, this ratio is lower than that we obtained in the phase two. That means when we allow the slab to slide, the acceleration to the slab will be less than the case when the slab is rigidly connected to the frame. So that's we can see clearly here. But when the frame goes to very high deformation, the ratio is become 1. Then this is our design base shear, that's here. Then we reach this about 3 times larger capacity. Then this shows the north column, center column, and south column, test 5, test 7, 10, the moment versus displacement response. So you can see at 4% drift, then we don't see any strength degradation for the column. Then after testing, so we remove one of the SBRB to put in the other machine. We have a 5,000 kilonewton unit actual tensile compression test machine here, as you can see moving around here. So we do the two-phase testing. One is the standard cyclic loading testing. Then the other phase is that we use the data we recorded from the shaking table. So we use that displacement input to this test machine to record the force. So then we use this, then we know, okay, what's the force versus deformation for this brace when this brace was in our 3-story frame in the shaking table. So we use this measure the response compared to the response we obtained from the shaking table. Because during the shaking table, we need to do the data reduction. So basically, we use a strain gauge to measure the column strength in order to calculate the column shear force. Then we have a total shear force. So then we subtract this column shear in order to get the brace shear force. So that's why. So when you see this, the two lines are very close. That means our data reduction is reliable. So finally, we plot all the shear force we have for the shaking table versus the roof drift. So we put this point here, measure from the phase 1 test and phase 2 testing. We also build a computer model to do pushover analysis. That's the solid black line, so to here. So you can see the test result we got at this point basically follow the trend. Then we do the testing at this level. So based on the code provision, it requires the ultimate displacement respect to the yield displacement should be larger than 5.5. But in our testing, we go to 11, but the building still not collapse. That means the column is strong enough, right? So if the column is strong enough, we use a moderate ductile column, but which can resist the very strong earthquake. That means current AIC seismic provision is very conservative for the rectangular box column. So in addition to that, my colleague will present you. We also use our testing facility to do a hybrid simulation for the box column and I-shaped column with UC San Diego and also Berkeley to do the model updating for this hybrid simulation. He will talk about in later. Then I will use this last slide to mention to you, we have a vision to build a new lab, the third lab for NCREE. The new laboratory will focus on the green energy. So because as you know, we are going to build more than 1,000 wind turbines along the west coast of Taiwan. So therefore, in this new lab, we have, this is the height of a building is 50 meters with a dimension 50 by 50 meters. So we have two very important facilities for this new lab. One is 480 G-ton centrifuge. I think this centrifuge will be very high capacity because in Taiwan now we have a very old centrifuge. The capacity is only 100 G-ton, which is already 30 years old. Now our government, our Ministry of Science and Technology Council want to support us to get this very high capacity shaking table for this centrifuge. in this case, we can get the soil condition from the 70 meter deep from the water level in order to study this soil property. In addition to that, we also try to build a facility to test this wind turbine blade, okay, either statically or dynamically. So the length we are proposing to do this testing is up to the 40 meter long. So this lab, now we are trying to get the budget this year. Hopefully the budget will be approved. Then we can start to purchase this facility and building this new lab before 2027. So if everything works well, so when you guys come to Taiwan next time, after 2027, so we can lead all you guys to visit our new lab, which is our new achievement in Taiwan. Thank you for your attention.
Yeah, so we have a time to hear this comment or question. In reality, so today, before yesterday, so in our ASEC TCCM, I advertised this session. We are going to have a very interesting presentation without any equations and formula and plot, but the first presentation included a lot of the graphs. But please, you consider his presentation is the keynote presentation of our session, okay? And as I told you, the purpose of our session is the introduction to each society's testing facilities, okay? So from now on, we will start our introduction presentation from Dr.
I will introduce myself. So. Okay, let me introduce myself. I'm Yohsuke Kawamata, working in NIED Japan. And in program, my title is like senior researcher. I guess nobody cares, but let me care. My correct title is chief researcher. So, today I want to introduce NIED's large-scale research infrastructure supporting a transformation to a resilient society. So first part of my presentation, I will introduce 3 large-scale testing facility, E-Defense, large-scale rainfall simulator, and ryospheric environmental simulator. And in the second part, I want to suggest something about constructing a great network of a large-scale testing facility. As you know, Japan is a country with various kind of natural disasters, including earthquakes, tsunamis, volcanic eruptions, landslides, windstorm, typhoon, floods, and snow and ice disaster. So National Research Institute for Earth Science and Disaster Resilience, it's my facility. NIED conducts lots of research with the basic goal of realizing a disaster resilient society. 3 years ago, we had 4 large-scale testing facilities, including this guy. It's called large-scale earthquake simulator, another shaking table. But unfortunately, it's out of order. So now we have 3 large-scale testing facility. So one is ryospheric environmental simulator in Shinjo, northern part of Japan, and large-scale rainfall simulator in Tsukuba, around Tokyo, and E-Defense. The former name is 3-dimensional full-scale earthquake testing facility, but even I don't remember. So please call us E-Defense. So first, I want to introduce from large-scale rainfall simulator and cyrosperic environmental simulator and e-defense. So a large-scale rainfall simulator in Tsukuba is very, very large, a large facility. But I never watched testing in real time. So this rainfall simulator has a very, very wide testing area. It's like 3,000 square meter. So we can place a specimen in this area. So we can place large scale specimen in the area. And we can simulate very, very heavy rainfall. We can adjust intensity of rainfall from 15 to 300 millimeter per hour. So in Japan, the maximum rainfall intensity is like 187 millimeter per hour. So this simulator can simulate about 1.6 times more than Japanese record. And this rainfall simulator is movable. So we can prepare several specimens at the same time, so we can save the time to perform more experiments. So let me introduce some test example in a large-scale rainfall simulator. I hope it works. So various types of sensors are installed in the slope, and we try to identify failure mechanism of slope during heavy rainfall, and we try to develop a kind of early warning system detecting a sign, I think first sign of a fatal slope failure. So slope height is 3 meters and gradient is 30 degrees. So you can see fatal failure of the slope. And next example is verification of structural resistance against impacts from landslide. In Japan, there are many houses in a landslide danger area. So actually, we observe this kind of damage many times. This movie does not have sound, so we build a very high slope, like height is 20 meters, and we pour 1 meganewton soil to build the slope. So let's see that again. Oops, just a moment. Oops, what happened? That's fine. Work. Oops. Okay. If you are interested in this movie, I will show you after this session. Please stop by me. So next large-scale testing facility is cyrosperic environmental simulator to simulate any kind of a natural disaster under cold weather. So this facility has lots of device to simulate lots of natural disaster under cold weather. 2 of snowfall machine, and rainfall machine, and solar simulator, and wind tunnel, and blower. I'm sorry. So let me show a first example of testing in a cyrosperic environmental facility. So the specimen is a special device, ultrasonic anemometers. So even under heavy snowfall, this kind of device need to work. So we try to continuous usage of this kind of special equipment under very heavy snowfall. So we can try to verify this kind of device by using this kind of snowfall simulator. And next one is testing of wind tunnel with snowstorm. So looks like this. So we place some structure model, small scale structure model. We can reproduce kind of blowdown and snowstorm. So we can find a great solution to this kind of disaster. And the last one, e-defense. I'm working here, so I can explain a little bit more than the other facilities. So e-defense is, let me say, one of the world largest shaking table. So area is like 20 meter by 15 meter, and payload is like 12 meganewton. And this shaking table is a 3-dimensional shaking table. And there are 24 actuators. So, and each actuator can control independently. So we can input rotation movement to a low PTO. So we call this shaking table is like 3-dimensional 6 degree of freedom shaking table. So because construction cost of this gigantic facility is like 450 million Japanese yen. No, 450 billion Japanese yen. So it's wrong. What is billion? Billion is 45 billion Japanese yen. I'm sorry. So it costs a lot. So we had a big motivation. It's 1995 Kobe earthquake. And we made lots of experiments, but we had another project earthquake in 2011, East Japan earthquake. So originally, defense was designed to simulate any seismic motion recorded in a Kobe earthquake. So we needed to upgrade of e-defense to simulate very long duration motion recorded in a East Japan earthquake. So after that, we had a big operation, a big maintenance. It cost a lot again. And by now, we had performed 124 series of experiments. So we have lots of experience about this kind of large shaking table test. So to get big money, we need big money to perform this kind of large scale experiment because construction cost of specimen is very, very expensive. We have to dispose of specimen. And now operation cost, like electricity and gas is getting higher and higher. So it's very expensive. So 15 years ago, we could find big funds relatively easily just to perform large scale testing to reproduce a great Hanshin Awaji earthquake disaster. And because we observe lots of fatal damage of old buildings in Kobe earthquake, so we made lots of research about seismic evaluation and retrofit for existing buildings. But these objectives are kind of past objectives. So now we are researching about indoor safety because furniture turnover killed lots of people. So we have to keep safe in room. So we are studying about these kind of things. And real-time assessment of structural damage status. I think it's one of the very popular topics now. And functional maintenance of structures and business continuity. So based on the past research, most of structures have reasonable seismic performance now. So we have to keep function of the structures now to keep a business continuity. And then in future, I think we have to think about disaster mitigation for regions, not in individual buildings. And also we have to think about multiple disasters and or cascading disasters. So because in Japan, we expect like Nankai trough earthquake and maybe Nankai trough earthquake induce big earthquake followed by tsunami or big earthquake followed by a subsequent large earthquake or something. So we have to think about multiple disasters and cascading disasters in future. So let me introduce some test examples in defense. Unfortunately, we checked this movie doesn't work because this movie is quite old. So let me skip it. If you are interested in this movie, I will show you after this session. And second example is functional maintenance of wooden residential house. So we build two houses, kind of full scale two houses. So it's a house, typical house in Tokyo metropolitan area. It's very narrow. The house built on very, very narrow land. So one is seismically isolated, and another is a house built on slope with some sewage pipes. So both house is seismic grade 3. It means seismic performance of these houses 1.5 greater than design code. So I think it's getting popular in Japan, grade 3 house. So because stronger house is rigid, of course. So in general, seismic energy is dissipated by deformation of the structures. But because of the rigidity of this house with seismic grade 3 is likely to slip. So because of large significant slippage, this kind of sewage pipe will be fatally collapsed. So it means structure itself is still fine, even after a big earthquake. This house lost the function. So when sewage function is like this, we cannot take a bath, we cannot take a shower, we cannot cook, so we cannot stay in this house. So it means function of this house is completely lost. So the last example is a real-time assessment of structural damage. So we build a 10-story steel frame building with external curtain wall. So we replaced 4 lines of LED light along the building. So you see two lines, a red line and 2 green line. So it indicates, this light color indicates damage status of each floor. So outside line is current. I think the outside line is estimation from current interstory drift. And inside one is the maximum interstory drift during shaking. And in this test, 23 external organizations used space inside of the structure. So I think from Taiwan, NCREE team and National Chengku University team is joined in this experiment. They install some duct on some facilities in this specimen. So an NIED large-scale experiment facility has 5 types of usage. So the top one is NIED own research. The facility are used by NIED. collaborative research, the facility are jointly used by NIED and external organizations. It's what we want to discuss. And facility rental, and contract research, and space rental. The space inside of test specimens is used by external organizations. I think this one can also possible options. So let me move to kind of suggestion for constructing effective network of large-scale experimental facility. So we are always expected to obtain research results appropriate to the research funds invested. I want to play with these big toys with no care to sponsors, but we cannot do that. So we have to think about that. So as I mentioned, large-scale experiments cost a lot. For example, one E-defense shaking table test costs like 100 to 300 million Japanese yen. It costs a lot. So it means we have to obtain the results with such big impact, such big funds, right? So we need to think about test result, research results with big impact to disaster risk reduction. So recently, advanced technology like digital transformation required to be used for disaster risk reduction in future. So there are many factors affecting the risk, disaster risk, and combination of these factors are infinite. So we need a burst of evidence under various conditions to verify that kind of advanced technology. So experiment can create a kind of example of artificial disaster. It can be evidence. So, but large-scale experiment have a very big advantage, which can minimize effects of scale and construction procedure. We can capture a very detailed localized response, but it's unsuitable for providing large amount of evidence because it costs a lot. So from a viewpoint of evidence accumulation, it's very important for us. So large-scale experiments alone is unlikely to produce a large number of evidence. So it means our result is not reasonable to the investment. So in order to establish effective network of large-scale experimental facilities, I suggest to, okay, let's think about a promotion of related research, such as small to medium scale experiments, numerical analysis, in situ investigation, and field observation. So rather than considering only the joint use of large-scale experimental facilities. So the next catastrophic disaster is coming any day, anytime. So we have to build kind of international research team for efficient evidence accumulation. So because each country has different engineering and social challenges, I don't think it's very easy, but I think let's look for a big theme leading to common goal. So everyone can get some benefit from this project. So in accordance with this big theme, joint use of large-scale experiments can be planned together. And of course, large-scale experiment costs a lot. So let's try getting money, research funds. Each team can try obtain research funding for large-scale experiments. And after the experiments, the data obtained from the large-scale experiment will be shared with ASEC members as reference data. So anyone can verify and validate with their research, related research. So evidence accumulation can be accelerated by these kind of activities. And so we have to build a data set. So all the results from large-scale experiments and related studies will be also shared. And for convenient usage of this kind of data set, we have to develop kind of common guidebook It specifies a research approach and what data needs to be provided, or something like that. So in a single chart, in a single diagram, putting everything in a single diagram, I think network will be something like this. So research group with large-scale testing facility are performing some large-scale experiments and provide reference data to a data sharing system. And research group with a large-scale testing facility perform lots of related research, and all the data will be put in a data sharing system, and we can make a kind of interlinked database. So anyone in ASEC member can access this data, and we can promote lots of related research. Let me summarize. I think my time is over, but let me summarize. In establish a network of large-scale experiments and joint utilization of large-scale experimental facility, I believe we have to discuss about various types of related research at the same time. So let's look for appropriate big thema which lead common goal, and large-scale experiment can provide reference data, and by constructing the data set, so we large-scale experiment and all related studies will be shared for anyone in ASEC members, and any researcher can make evidence-based verification, and this kind of verification and validation process can improve the quality of the data set. So this data set can be also utilized to validate and improve the accuracy of advanced technology for disaster risk reduction. I believe it's one of the most important roles of a large-scale experiment. Thank you very much for your kind attention.
Thank you very much. As I told you multiply, give me a second. Yeah, this is the first step of this TC29, and that means that this is the only for the introduction to the society's large-scale testing facilities. But thankfully, Dr. Kawamata gave us the solution already. Okay, I'm sorry, boss. In order to use the time efficiently, so I'm going to have a for time after all presentation. Okay, thank you. Yeah, thank you, Doctor. Yeah. Okay, please connect. Third presentation will be delivered by the Professor Julio Ramirez.
Yes, good afternoon. Can you hear me okay?
Give me a second. First, Julio,
Yes.
you need to share your screen with.
Don't you have to stop sharing?
Yeah.
Thank you. Tell me if you can hear, see my screen now. Thank you.
Yes, perfect. I can see you and.
Okay. So, good afternoon, everyone. It is my pleasure to be here today. Yes, I can see it.
Okay.
So you will be advancing the slides then? Is that how you want to do this?
Yeah.
Okay. So you tell me when we're ready and I'll start.
Yes, you may start. Perfect.
Thank you. And sorry about the technical difficulties. So I'm here to give you a brief introduction, and some of you are familiar with it, the National Hazards Engineering Research Infrastructure funded by the National Science Foundation. In the context of this committee's activities, I think it will touch on some of the aspects that have already been discussed. So I'll try to be brief, but to emphasize the importance of some of those aspects in looking forward to our collaborations. Let me please go to the next slide. Thank you. Keep on clicking until the animation. This is the only one I think that is animated. So thank you. So NIES was the precursor of NHERI, and some of you might be familiar with it. It was a 10-year shared research infrastructure that was funded by NSF, the National Science Foundation of the United States, focused exclusively on earthquake and related hazards. In 2015, upon completion of the 10 years of NIES, NHERI was established. It consists today of 12 components, and its period of award ends in on September 30th, 2025. Currently, the National Science Foundation is looking into what will follow NHERI. It could be probably known sometime next year or 2025, early 2025. So let me focus on the mission of NHERI, which is to enable research and educational advances that can contribute knowledge and innovation to improve the resilience of civil infrastructure against earthquakes, tsunamis, windstorm, and storm surge through shared access. The commonality between NIES and NHERI is the concept of shared access, and they are both distributed networks. And this is going to be very important for us in these discussions. May I go to the next slide, please? Thank you. This one shows currently NHERI consisting of 12 components. Of those 12 components, 8 are research laboratories focused on meeting the needs of external researchers that receive funding to use the facilities. I should point out, excuse me, the funding is applied for separately. Researchers write grants to the National Science Foundation or other federal agencies, or even sometimes industry, or a combination of all, to use these facilities. We have the laboratories that deal with testing related to earthquakes, such as the large-scale testing facility outdoor at University of California, San Diego, or associated hazards like tsunami, and that would be the Oregon State Flume and Water Basin testing facility at Oregon State. Then we also have mobile facilities. These are also very important, I think, for us in this collaboration, because they can mobilize to and have done so to various parts of the world. One is the geotechnical facility at the University of Texas at Austin, and the other one is the post-event reconnaissance facility, which supports researchers that go collect data after events. Deployments have taken place all over the world, as you would see in a subsequent slide. They provide equipment as well as expertise to teams of researchers that go and collect data. We also have 2 components. One is the cyber infrastructure platform of collaboration of NHERI. It's called Design Safe CI. It's managed at the University of Texas at Austin. And also another new facility since NHERI, since NIES, I'm sorry, is the Computational Simulation Center, so-called SIM Center at the University of California, Berkeley. Those 2 components I'm going to highlight here in subsequent slides. The reason being because they, I think, provide unique features to this network, which have been mentioned in other presentations in this session, such as computational simulation, the role of computational simulation in mitigating the impact of these hazards, as well as the data sharing and archiving components, which are very important. But I also will touch on another important aspect that these networks for collaboration offer, in addition to data sharing, simulation, and access to facilities, and that is the ability to educate the next generation of leaders in the field, researchers and engineers that will focus their efforts on making our community safer. I'll conclude with some summary regarding what possible avenues can exist for our collaboration. As I mentioned before, this is shared use facility, which means that each one of those components that I indicated, the laboratories in particular, and the cyber infrastructure platform, are open to external users. A key on this kind of access, as many of you know, is clear and transparent guidelines for that access, as well as charges, fees that will be assigned for using the facility. This is, if you visit DesignSafeCI, which is .org is the platform, you will find for each one of these facilities that are laboratories, information not only in their capabilities and efforts they have to train potential users, but also on the requirements with regards to fees for use of these facilities. I should point out that because this is funded by NSF, this network, which also includes wind testing facilities at Florida International University and University of Florida, because it's funded by NSF, researchers that get grants from NSF to use the facilities receive discounted fees access. Other agencies have to pay full fees because the funding to maintain and support the various components comes from the National Science Foundation. May I have the next slide, please? Thank you. Here, I briefly wanted to outline in 2023 the access that we had, the success with regards to this network. But most important, I want you to notice the photo on the right-hand side. That is at the outdoor large shaking table facility at University of California, San Diego. This facility over the last year has been upgraded to a 6 degrees of freedom testing facility. And also its capacity, you can see, is full-scale testing of up to 10 stories. In this case, it's a wood frame structure that was tested recently in San Diego. The testing, though, was for a grant from a researcher from Colorado State University, which is a different university. And so you can see here one of the key aspects of this network, that is the support that is offered to researchers from institutions that clearly do not have this kind of facility. As it has been mentioned several times, they are very expensive to use and maintain as well. So it is very important that they receive support from the government, that is true. But also another interesting aspect of this particular test is there were over 12 different companies associated with it. So industry support here is also going to be critical going forward. Diversified funding needs to be brought to bear to be able to use these kinds of facilities. And as it also has been mentioned, international collaboration is going to be critical, because duplicating these kinds of facilities, even at the level of countries, it is not feasible in many cases, and it's best to be able to develop some agreements for collaboration, and we'll see here an example in this presentation. May I have the next slide, please? So, for more information, one of the key aspects with regards to this type of infrastructure is the impact dissemination. Funding agencies, as it has been mentioned before, are very focused on what is the impact of the work that is being conducted. And it has to be at scale, right? So in this Journal of Open Access Frontiers in the Built Environment, you will find an ebook which you can download for free, as it is the case for open access, with 16 different articles, all focused around NHERI. And since it was published in 2021, you can see that it has received over 80,000 views and downloads. So this is a scale, a powerful way to communicate the value of the funding and the work of the research being conducted at these facilities. May I have the next slide, please? Thank you. On the subject of data sharing and archiving, this is one of the most important aspects, as he has mentioned also in previous presentations, of this kinds of collaboration. The value of the data is what people can do with it. And if it is not available outside reduced groups, that value gets severely limited. And also, the benefits from using that value are also constrained to a small group. The more participation, the more access to those data, the larger the impact of a network like this. And again, as he has been mentioned before, impact is key. It's what will motivate our sponsors to continue funding. So in the cyber platform for collaboration, Design Safe, there is a whole section dealing called the Data Depot that deals with making the data collected in various facilities by various researchers accessible to the public. You can today, without being even registered at Design Safe, which by the way is free, and it's a very short steps to become a member, it is available to you for downloading for tests that were conducted all the way to NIED to today. Yes, thank you. This is another example of the kind of data that is there. This is from the RAPID facility, which is the post-event reconnaissance facility at the University of Washington. You can see the extent of the data sets around the world that have been collected by various researchers with access to this equipment and facility. This data is available to you, again, also free. This kind of collaboration is essential going forward to really support the efforts of our community to mitigate the impact from these natural hazards. May I have the next slide, please? Thank you. Computational simulation has been mentioned before. The value of a large-scale testing cannot be minimized. It's essential for many reasons to investigate through collapse mechanisms, for instance, limit load capacities, to evaluate models that we have for modeling the behavior of these structures. But it's much more than that, right? Because again, as it has been mentioned before, the limits in large-scale testing could be overcome to the use of modern computer tools, which would allow, for instance, testing techniques such as the one that was previously described of hybrid simulation, but also simulation at a scales not ever been done before, regional scales. And as Professor Kawamata mentioned, that's the next step. We need to go from the one building to a community, to a region, and beyond now with regards to improving our mitigation techniques and other activities to protect our communities. This is being supported through the Simulation Center or SIM Center at the University of California, Berkeley, where tools are developed and resources that the community can use in their simulation efforts. Some of them are for regional scale type simulation, both for wind events and earthquakes. There are also training and educational efforts. This particular one is the NHERI Computational Academy, which was conducted this past summer at the Texas Advanced Computing Center in Austin. It was a partnership between Design Safe, our cyber platform component, and the Simulation Center, the SIM Center. May I have the next slide, please? And going also down to the student development. One of the key programs of NHERI is the undergraduate research experience. We found over 30 REUs, this is what the students are called, in cohorts of 3 that go to the various facilities and are mentored by a PI as well as a graduate student. These undergrads then gain experience in doing research. They have a big symposium at the end of, it's an 8-week experience over the summer, and they bring the results, and you can see the impact longitudinally of this kind of activity in how many of these students stay for graduate school, go on to get PhDs, and even today, after the 10 years of NHERI and the 7, 8 years of NHERI, NIES and NHERI combined, that some of them are now professors at universities that are coming back to use this research infrastructure. May I have the next slide, please? Graduate student participation while they are in NHERI, whether they are researchers or students from institutions, whether it's a NHERI facility, is also an important component. So we start the training at the undergraduate level, we continue the mentoring at the graduate level, both from the research that they do, but also from activities that are conducted in the network to also increase their experience and connections in preparing for whatever comes professionally after their graduate work. Next slide, please. And finally, with regards to education, focused on early career researchers, we have a summer institute, which is a 3-day program every summer where early career researchers and practitioners come and learn about proposal writing, about NHERI, about how to use NHERI to conduct research. And so all this experience is necessary because the impact of our networks is going to be multiplied many times over by the product, which are not only the data and the knowledge that comes from those data, but also the human aspects of the work that is conducted. Thank you. May I have the next slide? Another component that I wanted to mention that is critical for these large networks, and this goes to what it has been described with regards to collaboration, is a research agenda, a common research agenda, which in NHERI we call a science plan, the NHERI science plan. It basically is going to provide the justification for having such network. And that also allows to coordinate research. It provides focus for that research, and it also helps the researchers in writing their proposals. Our science plan was published in the 2nd edition in January 2020. And if I may have the next slide, we're working on publishing the 3rd edition. Both the 2nd and the 3rd edition are available in Design Safe. You can download them, they're PDF files. May I have the next slide, please? Click until the animation is complete. A couple more clicks, thank you. So this 3rd edition of the science plan, in addition to incorporating the information about the facilities and research campaigns, which are organized, coordinated examples of research needed to mitigate the impact of, in this case, earthquakes and windstorms and associated hazards, it will also bring 3 different new aspects. The first one is the social science component. And again, when we talk about resilience, having a social science component cannot be minimized. It's essential in order for us to truly improve the resilience of our communities. We can improve the resilience of our infrastructure, but without the human aspect, it's very hard to truly improve resilience of communities against this natural hazard. So Converge is a facility that coordinates that aspect, is one of the 12 components of NHERI. We are going to incorporate more that kind of activity in our science plan. Then is the 7 different networks that NSF has funded to do post-event reconnaissance and research after a major event. And those, some of them are well known, like YEAR. They have been around for many years for geotechnical aspects. There are others more recent, like STEER, which is a structural engineering network for research and reconnaissance, near event research and reconnaissance networks, and so forth. These different networks are separately funded by NSF, but coordinated through Converge. And the third important aspect in this new edition, which should be out sometime in September, is the incorporation of the tools and resources into the research that have been developed by the Computational Simulation Center, the SIM Center. May I have the next slide, please? Hybrid simulation has been mentioned before, and we think also that it is an important aspect of the future of testing in this area. This is an example of partnership that we do through NHERI with other awards of NSF. This particular one is a research coordination network called MEX for Multi-Hazard Engineering Collaboratory on Hybrid Simulation. This has been led by Professor Shirley Dyke. You can find more information about it, and it's about promoting and supporting the use of hybrid simulation, both real-time as well as quasi-static type hybrid simulation. May I have the next slide, please? International partnerships, and here we get to the point of our meeting today. We have a long-standing collaboration with eDefense, and Professor Kawamata showed this particular test of the two houses. Well, this is an example under the Tokyo Metropolitan Resilience Project, where an agreement between NHERI and eDefense, NIED eDefense, led to collaboration in research between US researchers, NHERI, and researchers at eDefense. The details of this program are well known. 4 major large-scale testing tests at eDefense. This particular one was the wood frame structure, where, as Professor Kawamata mentioned, the interest was more on related aspects to the resilience of a home that is already designed at the most modern standards. And this particular one looked at the interaction between pipeline and connections and the homes themselves. What do we do in these collaborations is listed there. We have some agreements with regards to access of facilities. This leads to improvements and new testing techniques, condition assessment. We also have aspects of research coordination, which is all something that has been mentioned before. Data exchanges are critical. This is something that needs to be discussed up front. It's very real to say we're going to share data. The devil is in the details. How long before it becomes public? Who gets access to what kind of data being generated? All these aspects need to be discussed ahead and have clear guidelines as to how this is going to take place. And of course, education and outreach. So if I may have the next slide, I can show an example of this research collaboration in 2019, which is when I think this shake table test was conducted. Next slide, please. Thank you. This is 2018-2019 effort. Here, researchers from 3 different awards received by NSF went to eDefense, and during the testing, they were focused on collecting new ways of collecting data using LiDAR and various other forms of measurement. They were supported by the post-event reconnaissance facility of NHERI, the RAPID facility. You can see the logo there. And this is led already to data being posted in the repository, as well as publications. And you can see in the slide towards the bottom there, the DOI that is associated with those data. This is available not only to US researchers, but also to our partners from Japan. In this particular test, it was led by Professor Nagai from Nagoya University. May I have the next slide, please? Thank you. And to conclude, basically our presentation is, I cannot overemphasize the importance of that research getting to practice. And this is one of the key activities in NHERI, which is promote the accelerated transfer of research to practice. We have a committee which consists of individuals, professionals that are in the area of tech transfer in the various aspects of NHERI work, and they work with our researchers to, from the beginning, to make sure that in their projects, they consider the possibility, I'm not saying that every research project leads to immediate transfer of that technology, but at least to have it in mind and also to bring practitioners into the team, which from our perspective are the end users of our product. So with this, I think in the interest of time, I will conclude my presentation and thank again everyone for this interesting session and look forward to working with you in making this reality of worldwide or at least global type research collaboration. Thank you.
Thank you very much, Julio. Now it's 5:26. We have only 4 minutes, but I couldn't stop the presentation by Julio because as you feel, the NERI program includes everything what we want to have. In reality, the model, what I want to make by myself in ASEC community is the very NERI. Do you agree? No. Yes. Yeah, absolutely. So I'm sorry, but as a chair of this session, and the most important role of the chair is to be punctual. So I will complete.
Good afternoon, and it's my honor to have this opportunity to give you a brief overview on the experimental activities we have in NCREE. NCREE is National Center for Research on Earthquake Engineering in Taiwan. So our General Director, Professor Chou, has just already give you some introduction about NCREE and NCREE's testing facilities and NCREE testing activities in his presentation. And now I will focus on some more, something like software support or software-wise development that we have developed in NCREE. So this will be my contents, and this is just a very quick overview. Your pointer is this pointer. Okay. So NCREE, sorry. In NCREE, we have two centers, one in Taipei and the other is in Tainan, in southern Taiwan. And in Taipei, we have a shake table. And we have another testing area we call reaction wall and strong floor system. And we also have a very dynamic system that allows us to perform dynamic tests on full-scale viscous dampers. And it is a single degree of freedom, but it has 200 tons dynamic capacity. And we have this MATS. It's multi-actual testing system. Actually, it is a 6 degree of freedom system that you can apply realistic boundary conditions on the specimens you want to test, whether it is a small frame or it is a component like a BRB, or you can do it like columns. In traditionally, you can do columns literally like you can drive its displacement at column top, but we're using MATS, you can apply the vertical load simultaneously with the horizontal displacement. You can also do tests like for multi-degree of freedom control simultaneously, unlike rubber bearings, so that you can apply actual load. The actual load capacity is about the maximum load it can apply is 6,000 tons. And in Tainan, we have an even bigger earthquake, which even bigger shake table. Its payload is 250 tons. In Taipei, that is an old shake table. It has 50 tons payload. And in Tainan, the shake table is featured as being capable to provide an earthquake that is generated from near fault. The source of the earthquake. And in Tainan, we also have BATS. BATS is a biaxial testing system. It's very similar to MATS. MATS is 6 degrees of freedom. Actually, BATS is also 6 degrees of freedom, but theoretical 6 degrees of freedom. But in practical, it can run only 2 degrees of freedom. That means you have a large enough displacement capacity and force capacity for 2 degrees of freedom. But theoretically, you can run 6 degrees of freedom. But for the other 4 degrees of freedom, the capacity is very limited. And in Tainan, we also have this wind turbine critical components. It's actually a small shake table that allows us to do tests on non-structural components. So these are the hardwares we have in NCREE. Okay, so with this kind of all kinds of this testing facilities, we can do a lot of interesting things like using the shake table. We have done a lot of interesting things like the one I'm showing here is the collapse test on our reinforced concrete columns. We also have conducted some interesting things like how to perform active control or passive control on the seismic systems using the shake table. And you can see that it's a real building, it's a school building. And before it is totally demolished, we ask for the government that we want to test it. So we do in situ cyclic test and hybrid pseudo-dynamic test using those school buildings, real school buildings. And this is Nyodo Bridge in North Taiwan. And you can see that, before it is demolished, we try to do the real test on the real specimen to discover the real capacity of any real system. So you can see that this is a bidirectional hybrid simulation. So because the target or the subject of our study, buildings or bridges, are very big and very heavy. So even with e-defense, we cannot do really very big test on real structures. So just as the professor mentioned that we need to perform a lot. So that's what we need to do a lot of other research. So this is one of the efforts that we are in this kind of hybrid simulation. The hybrid simulation means that we are combining structural analysis and structural experiments together to study the total dynamic behavior of a system. For example, if you can see that in this structural system, there is a peripheral frame and there is a BRB, a brace frame inside. And for this peripheral frame, they are calculated using a structural analysis program, just numerical simulation. But we construct and erect it to the specimen in our laboratory. And during the simulation, we combine the experimental simulation and the structural numerical simulation together. So that in this sense, we can make use of our very limited testing capability on the parts that really needs test, while we use the numerical calculation to calculate the parts that we have more confidence that we can capture it confidently. So this is hybrid simulation. So by this, we can try to make use of our testing facilities and try to study something interesting. And this is another hybrid simulation. So it is a full scale. You can see that it is a 3-story full scale brace frame. And so I'm I'll just skip it because I do not have enough. Okay, and in NCREE, we also develop a lot of interesting software. Like this one I'm showing is we have online model updating. That means I'm not sure. Do I need to explain that? But I'm afraid I do not have much time on that. But if you have questions, so this is a kind of we use the experimental data real time. When we do testing in the laboratory, we get data, and we use that data to calibrate our numerical model instantly. So that compared with the traditional numerical simulation, we are conducting a simulation on a numerical model which can change its property according to the experimental data we obtained in real test. So that's online model updating, so you can update your model when you do simulation. And we also develop some imagery measurements so that we can measure all kinds of displacement and strain field responses during our tests. And we also develop some online display systems so that we can facilitate remote participation and international collaboration. So when we do testing in the laboratory, we can immediately show the real-time data on the website. So anyone who has the links can see the results immediately, even if you're in the United States. So I've already shown you some of the testing events or testing activities we have in NCREE. You can see that the most important feature of this testing is that they are very diverse. They are we have different kinds of testing, and so. But you know, so as a laboratory guy, one of my problems is that in the past I always need to prepare a lot of different kind of control program and testing softwares, and for just a specific test. If there is a test requirement coming to me, I need to do the program. And once the test is finished, then the program I've done is useless, and I have to do the program every time when there comes a new test. So in this research, what we have put a lot of effort trying to develop one general purpose software that allows us to use that software so that we can conduct all the tests, almost all the tests we are asked to conduct in the laboratory. So the idea, I cannot go into detail, but the idea is that actually we try to, in the testing, there are a lot of concepts or activities or entities that's involved. And they are like this command generation, actuator control, data acquisition, and blah, blah, blah. And we develop some software packages that we can encapsulate all these hardware, software, or human behavior in certain software objects. And then after we have modularized all the concepts that's involved in test, and we can combine them together so that you can compose what you need based on your test requirement. So I'm sorry, I just cannot go to detail inside it. So these are the several something. Also make use of the internet so that we can connect different programs, integrate or make different programs connect with each other so that the programs can evolve independently. Some programs are very capable of doing structural analysis, but others can control this kind of testing hardware like actuator controller or data acquisition system, etc. And then we integrate them together with a unique, uniform communication protocol. And excuse me, how much time do I still have? 5 minutes? Thank you. So since I have only 5 minutes, I cannot go any further. So let me just right. See that. Right, using the software we have developed, we have done a lot of interesting things. Like this is an RC. CV means reinforced concrete container vessel. It's a part of the nuclear power plant. It's a 1 to 13 scale specimen. And in this test, we are using totally 12 actuators. But in NCREE, we do not have that big controllers that can simultaneously control 12 actuators. So we use our technology to combine several small actuator controllers together so that they can collaboratively to work together on this large test. And when the test is finished, they just go away. They serve different tests simultaneously. And that's the one of the things we have done before. And this is, we use this mass multi-actual testing system. It's a 6 degree of freedom system. We use that as a 6 degree of freedom actuator to conduct a hybrid simulation on this structural system. And most of the structural responses will be numerically evaluated using the computer program called PISA 3D. And for this experimental specimen, we tested using the maths. And we just test one SPD, that's mean steel panel damper, that's a specimen, and the data, experimentally measured data will be fed into for this 1, 2, 3, 4 elements. And but the experimental data will also be used to calibrate the material parameters for the other SPD elements. That means we can make the most use out of the experimental research data. And yeah, so that's real-time simulation. And in that test, we have different control modes and resisting force, but just need to go. Okay, and then you can see that this is in another year. We're trying to do this hybrid simulation again, but this time we are not using maths. We are using the traditional actuators. But for this test and the test that I just showed previously, they are very similar. Actually, we just need to switch a little the actuator control for this test, and everything can go directly. And recently we have done a very interesting simulation, which is yeah, you can see that this is the frame behavior we want to study. However, we only build this kind of this part in the laboratory, so that this part we tested. For the other parts, we simulated, and in that, so you can see that this is the specimen we have. We have 2, 1, 2, and 3, 4 actuators installed there, and we have 4 oil jacks there, so we can apply actual load on our specimen, and we use a very advanced method so that we can control the vertical force and the actuator and the horizontal displacement on the specimen. And to do that test, we can successfully capture the column shortening resulted from the column buckling from the experiment, and then use that data to feed into the structural analysis program so that we can have a very better simulation result from this test. Okay, so in this test, you can see the test result, and this is what one of our achievements here. That means we are using the force control to control the vertical degree of freedom. However, by using a fictitious force method, we apply a fictitious equivalent pulling down force, such that we enforce the numerical model to have that measure, the shortening in the column. And that test results show that we have successfully did it. So yeah, so I think I have already run out of my time, so I just stop here. So if you have any questions, I would like to answer, later. Thank you.